From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Everyone, today is such a sad day for all of us. Last class of the semester. You're all sad, aren't you? Oh, not supposed to be celebrating, you're supposed to be weeping. Yeah, well, all good things have to end, I guess. There are lots of handouts today. You have your homework's being returned for problem set 11, problem set 12. You have solution sheets for 12 and 13. You have the final exam from 97. You have the final exam from 96. And plus everything else I could find in my office I want to get rid of, I brought over here. It's over there on the table. So please pick up stuff before you leave. Also, we will end the class a little early today, so you can all fill out this evaluation form for the course. And then I'm going to ask for a volunteer who will put all these forms in an envelope and deliver it to Rick Shoemaker's office. And then he'll lock them up so I can't see them until after I give you the final grade in the course. Anyway, today we're on chapter 18, which is on Speckle. And it's a very interesting subject here. So 18, Speckle. So we're first going to do a little physical description. That's 18.1. And then we will look at some applications of speckle interferometry or speckle photography, sometimes it's called. Now, if we take a some diffuse surface, so let's make it just a piece of ground glass. Make it simple here. Ground glass. And this has a diameter d. And we're going to illuminate it with laser light. So, say coherent laser light. And we come over here a distance L to the right. We're going to find that we have a speckle pattern here, an intensity variation that looks like little spots. And if we think here for a second, what is happening here? Well, light's illuminating all these points here, and it's being scattered. And so we have light, any given point here would have light coming from all portions here. And while there's a random phase between these different spots due to the ground glass, this random phase is fixed with time. And so the light from all these points will interfere and produce some interference pattern over here. And if we think for a second, what's the highest frequency we can have in this interference pattern? Or in other words, what's the smallest speckle size we can have? Well, one thing we've learned in this course is that the size of the interference fringes, spacing of the fringes, depends upon wavelength, and it depends upon the angle between the interfering beams. And so we can say in going from one bright region to the next bright region here, The closest together that could be will be when d times, we're going to use small angles here, delta x over L is equal to the wavelength. So delta x is the distance here between a bright fringe and the next bright fringe. And delta x will be the smallest for light, interference of light coming from the edges here. And so the smallest spacing of the fringes, then it's just lambda L over D. Okay, so that's sort of what we learned almost the first day of class here. And so if I look at what's the maximum spatial frequency I can get here, well, it's 1 over delta x. And so that's D over lambda L, or I like to write that as 1 over lambda F number. So the highest frequency of the speckles that I can get here goes as 1 over lambda F number, or D over lambda L. So again, all these, the speckle pattern that we see here is just due to interference. Light here is coming from all points, and all these different beams are interfering, and the highest frequency will be produced by light from the edges of the ground glass. And if we take a look here at a speckle pattern, I would see something that looks like this. So here are the light and dark speckles, and again the highest frequency would be determined by this 1 over lambda F number. Okay. Now there are a lot of good books on this subject, and but I'll give you the best, my favorite reference here. I can find it in my notes. If not, I'll just find it in my memory, but I thought I had it here in my notes. And I'll just put it up here. There are a lot of good references here. My favorite one is a book that was edited by Chris Dainty called Laser Speckle and Related Phenomena. And the best chapter in this book, in my opinion, is a chapter written by my favorite author. Do you know now who my favorite author is? It might be Born and Wolf, but I don't know. Goodman, okay? Goodman has a chapter in here, and it's a very, it's actually the very first thing he did after getting his PhD. He went off to, I forget, Norway or Sweden over there, spent several months and worked on Speckle, wrote up a good section on Speckle, and then being a little bit like Shaq, he put it in his file cabinet and didn't do anything with it. And then Dainty came along and was publishing this book, and so he talked Goodman into maybe updating that work a little bit and putting it in his book. So it's the first chapter, I guess, in Dainty's book. Superb chapter on Speckle. So anyway, this is our speckle pattern here. Now, let's think a little bit what happens when we image this with our eye. In fact, I'll try to do a little demo here, and I'm not sure the people on TV will see this, but I brought a laser with me today. And I'm going to shine it on the wall here, and I don't know if you can see the speckle, maybe not, but then I'll take my glasses off, and then you have to tell me what you see. I'll make it, we'll enlarge it a little bit. Now do you see speckle? If you squint, what happens to the speckle? Can anyone say it doesn't do anything? Gets larger, doesn't it? No? Well, I don't know. To me it does. Doesn't for you. Okay, well, take your glasses off and try it. See if it does. I think a speckle gets a little bit larger, at least in my mind. It does. And let's kind of look at what's happening here. Those of you on TV, I'm sorry, you probably couldn't see that, but get a laser, shine it on the wall, and stare at it, squint, and hopefully the speckle will get larger. Anyway, if we go here, this is one of my favorite drawings in Goodman's chapter here, where we take this rough surface and we've illuminated it with a laser beam. And when we say rough, it's going to introduce OPDs that are a wavelength or larger. And now we're going to image that here. And this might be our eye imaging the surface on the retina here. And what we will get here is, well, each point is going to be imaged here. But we know there's some spread function associated with each point here. And so each point is going to be imaged here but spread out over some area. And so this is giving us the interference. So, you know, some points will interfere in a way to give us a bright speckle, and some points will interfere in a way to give us a dark speckle. And if we reduce the size of the aperture here, these point spread functions will get larger, and the speckle will get larger. Okay? So that gives you a little idea as to why you see speckle. Now, in the early days of the laser, people began seeing these speckle patterns, and they didn't like them. And so if you go back and look in the, maybe in the mid-60s in the journals, you find lots of papers where people tried to get rid of speckle. And whenever they got rid of speckle, it seems like they made the image worse. So maybe they didn't have speckle, but they ended up with a worse image. Finally, people realized, you know, what was causing the speckle, and it's awfully hard to get rid of if you're using laser, if you're using coherent light. So people said, well, we can't get rid of it. Can we use it for something? And there are several books written on using speckles. And I want to talk about 3 or 4 things here in class today, how you use speckle. And some of these things are useful, and some of these things are fun, okay? In fact, some are both fun and useful. Some are only fun. And this comes from the view graphs that you got at the beginning of the semester. So here's a case where we're going to be looking at out-of-plane surface vibration. And so we set up this interferometer. See, what's the name of this interferometer now? End of the course, the name is, looking like a grim time on the final exam. When is the final exam, by the way? What? I think I better check here. Well, we changed it back to the 14th. Wait, if you want to come for the 12th and wait for it, you can. So the exam is on the 14th, May 14th. And on the exam, if I ask you what kind of an interferometer is this, you will answer? Deployment green. Whew, good, good. Okay. And so anyway, what we have here is a smooth surface and a bright vibrating surface here, diffuse surface. And if we look at the fringes we get here, diffuse, we're going to get a speckle pattern here. And it's going to be vibrating, and assuming it's vibrating fast compared to the response time of the eye, so we're going to see a time average of the vibration here. And maybe you don't know the exact form of the speckle contrast here, but you know when things are vibrating, you're looking at fringes, there's something that always pops up. It's a J0 Bessel function. Someplace it's always going to be in the answer, okay? And so it's going to go as J0, and here we're going to have the optical path difference, and so it's 2 pi over lambda, normal incidence, 2d, amplitude here, and then what's important is d in units of wavelength, so it's going to be 2 pi times 2d over lambda. And the rest of it, well, that's a little harder to maybe derive, but the thing is, whenever you think of vibration, I want you to think of zero order Bessel functions, okay? So I have some pictures here, and I have to tell you, you have to use, well, is your imagination good today? This is very important in looking at these results. Otherwise, it's going to be a failure. Okay, turn on the imagination. And on the left here, the plate is stationary. And we see a lot of good contrast speckles. And then I'll take a sip of coffee before I go to the results here. Okay, on the right now, the plate is vibrating. And in some places, now I like to just zoom in on this. Just zoom in. We need all the help we can get on this, actually. Good, thank you. Some places, the fringes are kind of washed out, like there. And in other places, like here, where we're at a node, we have good contrast fringes, good contrast speckles. Can you see that? First we're on the final exam. Could you see it then, do you think? Yeah, then you would see it. Okay. Well, the original picture, I'd have to say, looks a lot better than this. But anyway, if I stare here, I can see that the contrast is low here and high there. And so the contrast will depend upon the amplitude of the vibration. Okay, so that was one application of speckles. And we'll get some better results before we get done here today. Another application, which I'm not sure it has any use at all, but I've had a lot of fun with it over the years. And here we're going to talk about in-plane displacement. What we're going to do here is we're going to make we're going to take some object here. For simplicity, I'm going to take a piece of ground glass. I'm going to illuminate it with a laser beam. I'm going to get a speckle pattern over here. Now I take this ground glass, and I'm going to record the speckle pattern on a piece of photographic film, let's say. Now I'm going to take this object and translate it sideways, a small distance, in plane displacement. What's going to happen to the speckle pattern here? The first order, anyway. Illuminating this with collimated beam, move this sideways, the speckle pattern will move sideways. Okay? I'm going to make a second recording. So what we have here will be two recordings of speckle patterns. The two speckle patterns are essentially identical, but displaced. Okay. So now I'm going to take this recording, I'm going to process it, process the film. So I have a density recording, and I'm going to put the film down here. And I'm going to illuminate this film with a laser beam, put in a lens, and look in the focal plane of this lens. And what I will see in this focal plane will be interference fringes. And we can explain these interference fringes two ways. First, we have the Gasco approach, okay? And the Gasco approach is we have an amplitude transmission here, which is some function of x, actually x and y, but just one dimension, some function of x. And we have two identical speckle patterns here. So superimposed on here, we have something that goes as a of x, and something else that goes as a of x minus x naught. X naught is how much we've moved this between the two measurements. So two identical patterns here, but they're shifted relative to one another. So I'll take a Fourier transform of that, and I'm assuming it's a linear recording process, although that ends up, that wouldn't matter. But for simplicity, let's say it's linear. So the amplitude transmission here is proportional to the exposing intensity. And so I have the pattern plus a shifted version of the pattern. And so if we take the Fourier transform of that, well, I have the Fourier transform of a of x, which is some random pattern here. And I have the Fourier transform of a of x minus x naught, the shifted. So that's another random pattern, but the difference in the Fourier transforms is from Gasco would be from the shift theorem, a linear phase shift. So we have these two complicated messes here interfering, and the two complicated messes are the same except for a linear phase shift. Well, the linear phase shift depends upon how far this was shifted between the two exposures, and it depends upon, it's linear with spatial frequency. So lo and behold, what we're going to get will be nice, straight interference fringes. The spacing of the fringes will be inversely proportional to how much this has been shifted. It's going to be proportional, the spacing will be proportional to this focal length. And always fringes will be, spacing will be proportional to the wavelength. So the spacing here goes the focal length times the wavelength divided by how much we've shifted things by here. So that's from the linear shift theorem. Any questions on that? So that's the Gaskell approach. Now we do the Weyand approach. The Weyand approach is that, let's see, we learned at the beginning of this course, we learned about Young's two pinholes. And when we have two pinholes, we get the light from the two pinholes give us straight interference fringes. And this, again, the spacing of the fringes would be inversely proportional to the separation of the pinholes. So what we have here is, when we record a speckle pattern, we have a whole bunch of pinholes here. A whole bunch of pairs of pinholes. And so these pairs of pinholes will give us these interference fringes. And again, the spacing of the fringes is inversely proportional to the spacing of the pinholes, proportional to this focal distance here, and proportional to the wavelength. So both the shift theorem and thinking of this as Young's two pinhole experiment gives us the same result for the basic fringes we have here. Now we have a whole bunch of these Young's two pinholes experiment, two pinholes here. So superimposed on these sinusoidal fringes, we're going to have some speckle pattern here, which we'll see in a second. So the next is just some results that I actually did myself a long time ago when I did this experiment. And so these are our fringes. And so the translation was in this direction. I can't tell you this way or this way, but the translation was this way. And if we knew the wavelength and the focal length of the lens, I could measure the spacing here and determine how far the plate has been translated. In the center, well, we get a lot of light that goes straight through the system, a very bright spot in the center. And so we get a bright spot here in the center. Now, if in the reconstruction process, if I used not a laser beam with single wavelength, but if I used a spread of wavelengths, what would I get here? Well, I would get the same thing except, well, and all the fringes would give me a bright fringe at the center here. But then, as I moved out from the center, I would get different spacing fringes for different wavelengths. The red would be more widely spaced, and the blue would be finer spaced. And so you can actually get some very pretty patterns here by using white light to reconstruct this. You don't have that many fringes here, and so you can go out here a ways before the different wavelengths get out of step and the fringes wash out. Okay. Any questions on that? Well, there's another experiment we could do, is that instead of making an exposure, moving the ground glass sideways and making a second exposure, what we could do is to oscillate this back and forth and make a time average exposure. Okay? Then what do you think we'd see down here? Well, if we oscillate this sinusoidally, what we're going to see something down here that some way is related to that zero-order Bessel function. Okay? Contrast some way would be related to that. So what we would see here would be something, so I'm oscillating this way with some amplitude. I will see a pattern, maybe it looks like this. So my oscillation was this way. And the contrast here is going to some way drop off as that zero-order Bessel function. And so the fringes are narrow in the direction of oscillation. And the more I oscillate here, the more narrow this would become. And then you could think of vibrating this not in a linear fashion, but you could vibrate it, in some plane here. And here's an example where they claim they oscillated this in a figure of 8 motion. And anyway, they got a pretty pattern. And the real original picture is very, very pretty. So anyway, you can measure in-plane vibration here. Oops. You can measure in-plane vibration or translation and get some pretty results, and maybe even sometimes even useful results. Any questions on that? Continuous exposure, right? If the amplitude is too much, speckles will just average out to 0. But if we have a small enough amplitude, we'll get some very pretty patterns in the Fourier transform plane. Okay. Now, there's probably the largest application of Speckle interferometry has been stellar Speckle interferometry. So let's talk about that for a second. And the problem we're trying to solve is the following. We are on the ground here looking at some stars. And we would think that the larger we make our telescope, the better the resolution is of the star or the planet, whatever it is we're looking at. And the problem is that the atmosphere is between our telescope and the star or the planet. And the atmosphere introduces some aberration, turbulence, aberration in the system. And so as we make our telescope larger, the resolution gets better until we get to a diameter, well, it depends on where we are on the Earth, but the typical number that people use is until we get to a diameter of 4 inches or 10 centimeters. And then as we make the telescope larger after that, it's true we collect more light, but the resolution doesn't really increase. And if you go back and look at the resolution of an aperture 10 centimeters in diameter and use visible light, you end up with a result of a resolution about 1 arc second. To give you an idea what an arc second is, certainly it's not very large, but it's an arc second would correspond to, I think it's 1 foot at 39 miles away. So as we make the telescope larger, we just don't get any better resolution unless some way we correct for the atmospheric turbulence. And that's where adaptive optics have come in, or we put telescopes and satellites, some way to get rid of the atmosphere. But there was a very clever Frenchman by the name of Labouré who came up with this idea of stellar Speckle interferometry. And what he said is that if I look at a star, I can see speckles. In fact, I'll show you a picture of a star where we do certain things so we can see the speckles. This, believe it or not, is a picture of an unresolved star. And you see all kinds of speckles in here. He said, I can see these speckles if I do a couple of things. One is, well, the atmosphere is changing at some rate, so I have to make my exposure short enough that the atmosphere does not change during the exposure. And so the time typical numbers that you need are like a millisecond or a few milliseconds. And then you freeze the atmosphere. So that was one condition to see these speckles. The second condition is, well, I have to make the spectral bandwidth small enough so the coherence length is long enough that I can see speckles. And that turns out to be about 100 angstroms or 10 nanometers. If we pick a spectral bandwidth of 10 nanometers or less, we take a short enough exposure, a millisecond or so, we look at an unresolved star, we will see these speckles. Now, the thing is that the speckle size here is determined by the wavelength and is determined by the diameter of the telescope. And these little speckles here are like the airy disk. They may not look like airy disks, but they're down to the size of the airy disk you have for the telescope. Okay. Now, the overall size here is determined by the atmospheric turbulence. It spreads out the overall size. So what he is saying is that the speckle size is determined by the wavelength and the telescope diameter. And so while the overall blur is set by the turbulence, the speckle information is limited by the resolution limit of the telescope, not the atmospheric turbulence. So the clever guy said, well, some way this information is in the speckles and information about the actual size of the star. And if I make the telescope larger, I will get smaller speckles and I can get more information. So there has to be some way of getting this information out of the speckles. And so the following is what he did. And this, a lot of people have done this experiment and it works very well. In fact, some of the leaders in this are at Kitt Peak here. Anyway, this is the procedure that he came up with. He said, well, let's take a large number of short exposure photos of the object, where between the exposure time, we wait long enough for the atmosphere to change. So we'll get many pictures of this star where the speckles are different for each picture because the atmosphere has changed. Then he said, well, let's take the Fourier transform of each photo. And we'll show some pictures of this in a second. But we'll take the Fourier transform of each photo. And in this Fourier transform, we have both phase and we have amplitude information. We're going to throw the phase information away. And we're going to record only the amplitude or the square modulus of the amplitude, i.e. the intensity of each of the Fourier transforms. Okay? We've thrown away the phase. Then what we're going to do is to average up a whole bunch of these. So each one of these star pictures is different, and we're going to add up all these diffraction patterns. And then he says, well, let's take the Fourier transform of this average of the diffraction patterns. Now we're throwing away the phase information up here. We got the squared modulus. So when we take the Fourier transform, we do not get the original picture or the original star back, but what we will get, again from Gaskell's course, we'll get the autocorrelation of the image. And so, and if we average up enough of these, we're going to get the autocorrelation of the diffraction limited image of the object. And I have some results here. This is a laboratory experiment. It wasn't real stars, but if we can stare here for a second, maybe we can see this. Maybe I'll pick this row down here. So here we started out. This was a binary star, simulated binary star. Okay. This is a photo of that. So we have atmospheric turbulence, and so we have a speckle pattern here. And we're going to take the Fourier transform of that. Okay. And then we're going to sum up, we're going to repeat this, for this example, 20 times. In real life, it might be 100 or a few hundred times. We're going to repeat this. And then average these guys. And all these, these are, speckles are random here, but when we average them up, they're going to average out here, and what we're going to get will be a nice pattern that looks like this. So it's a Fourier transform here. Now, if this speckle pattern, binary stars, there should be pairs. It's hard to see here, but there's pairs of speckles here because we had two stars. And so when we do the transform, we would get interference fringes. We see it here. Maybe we see it better up here, actually. And now if we take the Fourier transform of that, and we've thrown away the phase information, so when we take the Fourier transform again, we don't get back to the original object, but we get back to the autocorrelation of the original object. So this turned out to be very good at looking at binary stars. And when they went to the 200-inch telescope, they actually were able to get out to the aberration-free diffraction limit of the 200-inch telescope, even in the presence of turbulence. But again, you don't get back the original object, you get back the autocorrelation of the original object. So again, the whole idea is you have a random speckle pattern here, and we will just Fourier transform that and sum up a lot of these, and the random part will tend to cancel out. And we'll get back to the diffraction limited MTF of the telescope system. Any questions? Well, again, if you go to Dainty's book, there's another chapter in there on by Dainty on this subject, and in a little bit, it's a little bit dated now, but it still gives the basic ideas for it. Where it's dated is that early days they did all this optically, and of course nowadays what they would do is this photo here would be on a CCD, and all the processing here is done with a computer as opposed to optical techniques. Same basic theory though. Okay. So back in my early days of working in industry, we were trying to look at Russian satellites. And we tried Speckle interferometry, and we found out this worked great if Russian satellites looked like dumbbells. But when they got to more complicated satellites, when you take this autocorrelation function, you get a complete mess here, and you can't tell anything about the satellite. But anyway, it was fun playing anyway. Nowadays, you want to see a Russian satellite, you just go out and buy one, I guess. Okay, next topic. Still on Speckle. This is going to be electronic speckle pattern interferometry, ESPI. And we're going to do speckle techniques here, but we're going to use a TV system to record the speckle instead of film. And the advantage here is that it's going to give real-time measurements. The disadvantage is that the speckle size is going to be limited by the camera resolution, so we're going to have large speckles. And the nice thing is that we can do some type of computer analysis of this speckle data. And so the classical setup for doing this is the following. We have a TV camera looking at our speckle pattern. And you can basically do anything here that you could do with holographic interferometry, except it's at a much lower spatial resolution. So for example, we could have some object here, and getting speckles from that, and we could store the speckle pattern here, and then we could deform the object to get a new speckle interference pattern. And now if we subtract the original pattern from the original pattern from the new pattern, new speckle pattern, we're going to get a result here that looks like interference fringes for deformation. Okay, so it's this stuff is just like holography, except we're not using film, we're using a TV camera to record the interference pattern. So we could measure deformations here. Or something else that I have results for, I'm going to show results for, is we have an object out here that's vibrating. And vibrating fast compared to the response time of the TV camera. And so we're getting this time average speckle pattern here. And then we can do some spatial frequency filtering of that speckle pattern, which is similar to what we do in holography when we select the first order. And we can get a pattern here that looks like this. These are some time average vibration patterns obtained using SPI. So these are plates that are vibrating, and the bright here would be where the nodes are, and the dark would be where the speckles are averaging out. Okay. Again, we will always have fairly large speckles here because the TV camera has to be able to resolve the speckles. And while with film you have thousands of lines per millimeter of resolution, with a TV camera you might have 500 by 500 points of resolution or so. So they have large speckles. But the nice thing here is that we observe this real time. So as I change the vibration out here, on the monitor here I can see how the pattern changes in real time. Okay. Well, there was a time when I got very interested in this and played with it a fair amount. And I had one student, Kathy Kreth, who did her PhD on this. And instead of calling it electronic speckle pattern interferometry, we called it digital speckle pattern interferometry, DESPI. And this was done quite a while ago in '85. Computers and CCD arrays and whatever were not nearly as nice back then as they are now, but she still was able to get some pretty interesting results. So I went back to her old dissertation, and I have taken out a few pages that I want to show you. So let's first look, and I didn't give you a handout here, but for those of you who are really interested in this, you can go back and look in her dissertation. The setup she did was something like this. She had a helium neon laser, and some way went by here, and we're illuminating some object. And this object is going to vibrate, or it's going to deform or something in a minute. And the light from here went through here, and so this camera, CCD array, is imaged onto the object here. And put a mirror in here to vary the path difference, mounted on a PZT, so we could do some phase shifting stuff if we wanted to. And now to get the interference here, well, the CCD array has low resolution. In fact, in 1985, what we had really low resolution. This was a 100 by 100 array that she used. Nowadays, you probably use a 1,000 by 1,000 array, but 100 by 100. So it had a very low, had a small speckles. They had a small angles of interference. And so she brought in a reference beam here through a fiber and put that in the center of the aperture. Now this aperture could be closed down to make the speckles larger. And then this, so we got speckles from here, and then we interfered that with a reference beam. Okay. I have a picture of this, but I don't think it will show up. But there's one point in the picture I want to make, so I'll try looking at it anyway. I don't know if we can zoom in on this. Probably not going to be able to see it on the TV. I can see it on the picture. Nah, no way. Okay. Anyway, I'll describe what I wanted you to see. There's a fiber coming through here, and there's a needle holding the fiber in place. But the whole point I want you to see is clay was holding it together. I feel that in any laboratory experiment, the two most valuable things in the lab are clay, and what's the second thing? Duct tape. Well, close. I was going to say double sticky tape, but now I have to warn you though, if you ever start a company and begin selling products commercially, the clay has to go. You can't, customers just do not, they will not pay as much money for instruments held together with clay as they will if you use bolts and things like that. But for laboratory, clay and double sticky tape are great. Okay. What we're going to do now is we're going to look at a case where this object is going to deform. And for our first case, the deformation is just going to be a little tilt here. And so we take this into the computer, and we're going to look at the fringes, and we're going to take two fringe patterns here, speckle patterns. One is before the object tilts, and the other one is after the object tilts, and then in the computer here we're going to subtract the two. Okay? And that's what we have here. So very coarse speckles, because when we did this we had only a 100 by 100 element array. And so this was a speckle interference pattern recorded before the object tilt and then after the object tilt, and we subtracted the two, and those are the fringes you see. Well, fair contrast, probably actually looks better contrast than what it did in real life. But we can make it a little bit better than that. And the whole idea here, averaging, okay? So what Kathy did was she repeated this experiment where she recorded a lot of pictures of this before it was tilted with the beam illuminating at slightly different angles. Stepper motor change here, so a little slightly different angles. So we had, what number did we use? 10 data sets. So we had 10 different speckle patterns down here stored in the computer. Now we deform the object, and again by deformation we mean just tilting the object in this case. And we used the same 10 angles of illumination here and got 10 more speckle patterns. And then we subtracted the first from the, first before deformation from the first after deformation, and the second before from the second after, and so on, and got these 10 sets, and then simply added those up. And now we got something that looks much better. So that was averaging 10 sets of measurements where the speckle pattern changed between the 10 sets. And so the point I wanted to make here is averaging helps enormously. Okay. Next case here is a similar thing. I won't go through all the details of how we got to this, but now the again it's well, what we did here, I guess we first recorded what the speckle pattern looked like with the object with the reference beam vibrating, or and so the interference between the two beams canceled out. And then we stopped the vibration and took the difference and saw the deformation here, and then repeated the same thing, same approach before, using 10 data sets. So basically just a little different deformation. Yeah, I'll skip that one. What we're going to do now is to look at a surface again where we're measuring deformations. But now what we're going to do, I mean, once we get this data in the computer, we no longer have to just look at the fringe patterns. We could actually analyze the data. And so we can do phase shifting approaches here with speckle pattern. And that's why we have this PZT mirror mounted on a PZT. So we're going to get a speckle pattern here. We're going to measure the phase across that pattern, which is going to be a complete mess. Then we're going to deform the object. In this case, deformation is, again, just tilting here. We're going to tilt the object, and we're going to get another speckle pattern. We're going to measure the phase across that using phase shifting. And again, we get a complete mess. But now when we subtract these two messes, what we're going to be left with is only how the object has changed, i.e. the deformation. And so going through that, we get nice contour map here of showing how the object has been deformed. While for each measurement here we had a completely sort of random phase variation due to the speckles, that when we subtract the two measurements, what we see is only the difference between the two. So the random part drops out, and we're left only with the tilt. And again, once you get this in the computer, you can do all kinds of data analysis on that. And one last one here is where you Well, this is looking at fringes due to deformation. So we did a speckle pattern, deformed the object, another speckle pattern, and the computer took the difference. And also, we used phase shifting to measure the phase of the speckle pattern, both before shifting and before deformation, after deformation, and you end up with a contour map that shows you what the deformation was. Okay. So the result here is it's pretty powerful way. Once you get the data into the computer, these speckle techniques are pretty powerful for measurement of vibrations, measurement of deformations, and I think now that detector arrays have higher resolution, you can easily get 1,000 by 1,000 element CCD now. Computers are much faster. This is can be a pretty good approach for measurement of deformations and vibrations. Any questions on that? Well, the last thing I wanted to do today is I have a really favorite homework problem here, which I like to give, but the problem with giving it is that we never cover the material until the last day of the semester. So it's hard to give a homework problem. So I thought I would spend a few minutes here talking about this favorite homework problem of mine. And it's I think it's the last problem in the homework sets that I gave you. And I brought along here a copy of it, and we'll read it and explain what it is, and then we'll see if we can work the homework problem there. I have a piece of ground glass of diameter D, and it's illuminated, say, at normal incidence with a monochromatic collimated beam of wavelength lambda. And the resulting speckle pattern is recorded on film, a distance f away. So right down here, here's my piece of ground glass. I'm illuminating it first with one beam, and I'm getting a speckle pattern here. Now I make a second recording of the speckle pattern with a collimated incident beam at an angle theta. So now I change the angle of illumination and make a second recording here. Okay. Assume that after processing, the amplitude transmittance of the film was proportional to exposing irradiance, and the resulting film transparency is illuminated with a collimated plane wave of wavelength lambda sub I. A lens of focal length f sub I is placed after the transparency, and the light distribution in the focal plane of the lens is observed. And then we have a number of questions to answer, and I want to assume small angles. I don't have to worry about sines and tangents and stuff. I just use the small angles. Okay, so we've recorded here speckle pattern, changed angle of incidence, made a second exposure, processed the film, put it in place, illuminate it with a different wavelength, look in the focal plane of the lens, and we see something here. Okay? And maybe from what we've talked about today, maybe we can almost guess what we'll see there. So let's think first. We got these two speckle patterns. One is beam coming in like so. Second one is beam coming in at an angle. What's the difference between these two speckle patterns? They're the same, essentially the same, but shifted by some distance. If this angle changes by theta, how much are these shifted by? Focal, I'll give you a hint. Focal length f, angle of theta. F theta, okay? So they're separated by some distance f theta. If this has a diameter of d, what's the maximum spatial frequency recorded here? Well, it's d divided by lambda f. So it's d over lambda f, what we had earlier today. Okay. So max frequency, nu max, is d over lambda f. Okay? And so what we're going to get here, we're going to get we're going to get a set of fringes. Just like what we had earlier today, when in that case we recorded a speckle pattern, translated it sideways, recorded a speckle pattern. Same thing here, just now shifting the speckle pattern by changing the angle of illumination. So we're going to get a set of interference fringes here. The light here is going to be spread out over some area, and if we assume a linear recording process, the maximum spatial frequency was d over lambda f, and so the spread of light here, spread of light in the focal plane, is going to be, well, it's going to be whatever this focal length is here, f sub I, times whatever wavelength is lambda sub I, times this maximum spatial frequency. Okay. And what we think we get plus or minus orders here. Okay. So the spread would be plus or minus that. So the plus or minus orders. And so that's going to be equal to plus or minus f sub I, lambda sub I, d over lambda f. Okay. I don't care so much about the answers. I want you to understand where that came from. So the highest spatial frequency is going to determine how much it's spread out. So it's going to be lambda. The angle of spread will be lambda times the highest spatial frequency. Distance will then be the focal length times that. We get plus or minus first order, so we get a plus or minus here. Okay? So that's the spread of light in this focal plane. Okay, so part A was supposed to find the fringe spacing in this focal plane. And I think we can get the fringe spacing. Is going to be lambda sub I, f sub I, over the speckle displacement. So the distance between the speckles, so Young's pinholes, or shift theorem, whichever you like. And so that's f sub I, well, lambda sub I, f sub I, over f theta. Okay. Part B was how many bright fringes can be observed in the focal plane. And there's a little more to part B, but that's the part I'll do here. So number of fringes, slide this up here. Is it, well, you're going to get one bright fringe in the center. Okay. And then you're going to get other fringes spaced plus other fringes spaced lambda sub I, f sub I over f theta. And so the number of fringes is 1, the center fringe, plus the spread of diffracted light divided by the fringe spacing. Okay. And so that will turn out to be 1 plus 2 f sub I, lambda sub I, d over f lambda, whole thing divided by lambda sub I, f sub I over f theta. And so that turns out to be 1 plus 2 theta lambda over d, if you go through the arithmetic here. Okay. And so if we have bright fringe at center, if bright fringe at center, and edge, number of fringes equals 3. And so 3 is 1 plus 2 theta lambda over d. And so theta is lambda over d. So for the condition of having just a bright fringe at the center and one at each edge, the smallest, the theta for that will be lambda over d. So that's kind of saying here that we get the same resolution here as what we get with a regular telescope. And so my last part of this question was, the results of this question imply that as far as resolution is concerned, all telescopes can be replaced with ground glass optics. What's wrong with this statement? We got the same resolution here with this piece of ground glass that we get with a telescope. So why do I need to make good telescopes? Why can't I just replace all the telescopes with ground glass? Well, the answer is, in order to get good contrast speckles, you have to have good coherence. To have good coherence, in order to get good contrast speckles, the optical path differences must be less than the coherence length of a source. So we have to have short coherence with a ground glass telescope, and short coherence means narrow bandwidths. Narrow bandwidths mean not much light. So the real problem is you don't have much light. It's true you get the same resolution, but the amount of light that you get is pretty small. And so fortunately, the telescope makers still have a business. Anyway, I always thought that was kind of an interesting problem and fun to play with. Well, I think my time's about up because I need to give you 5 or 10 minutes to fill out this form. First, I hope you've had fun in this course. I certainly enjoy teaching this course a lot. I think the whole area of interference and diffraction is, for me, it's a very exciting area. It's a lot of fun to play, and I hope your feeling is the same. It's interesting material. So anyway, the final exam then is, what was the date? The final exam was what? 14th. Okay, May 14th. What time in the day? 6 a.m. was it? I forget. No, 8 a.m. That's right, 8 a.m. And be in this room. Okay, and so the exam will be similar to what the other two exams were. And as I always say, you get an A in the final exam, you get an A in the course. Okay, so what's that?
That was cumulative over everything.
I gave you at the beginning of the semester how the grade would be calculated, but I'm saying that I will calculate it that way. Oh, the material in the front, yeah. Let me finish. I will calculate it that way, except that then I'll look at your grade on the final exam, and if that raises your grade, I will raise your grade in the course. The final exam will cover all the material in the course. I'll try to make it fairly uniform for all the material in the course. Any other questions? I need one volunteer who is willing to carry this envelope back to Shoemaker. If not if I can't find one, I will. He knew I was going to point towards him. Right. Okay, so we'll hand this out, and then I'll give you the envelope.